variations on a theme, and the theme for today is going to be heap. So let's first look at a couple of problems that can all be solved using heap structure, and then we're going to go into more detail on the properties of the heap, how we can use it, and how the heap pertains to those problems. And then later on we're going to find the variations of that theme as they solve those problems that we are looking at. First problem is LeetCode 767, reorganize string with the difficulty level medium. Reads, given a string S, check if the letters can be rearranged so that two characters that are adjacent to each other are not the same. If possible, output any possible result. If not possible, return the empty string. Comes up with two examples, S equals AAAB, and the output would be ABA. Second one is SAAAB, and there's zero output because there's no way that not two letters A are adjacent to each other. So it's like no matter where you place the B, there's always going to be like two A's adjacent, and therefore there's no result. Next one, and that's basically the key to most of the standard heap problems, is to look for these top k or top n most frequent n closest n largest elements. That's always like a big sign for a heap-based solution. So let's have a look at that. 973, k closest points to the origin. We have a list of points on the plane. Find the k closest points to the origin, 0, 0. Here the distance between 2 points on a plane is the Euclidean distance, which is the square root of the sum of the two squared elements. You may return the answer in any order. The answer is guaranteed to be unique, except for the order that it is in. Example 1, points 1, 3 and minus 2, 2, and find the one closest points. So it's just the closest one. Output minus 2, 2. With the explanation that the distance of minus 2, 2 is smaller than the other one. And number 2, points 3, 3, 5, minus 1, minus 2, 4. K equals 2. Output 3, 3, minus 2, 4. Because now we're looking for the two closest points, or like two smallest distances, right? Ruling out 5 minus 1 as the largest, furthest away point. And then some notes on the maximum amount of points given, and then like the maximum distance possible given those points. Next one is design Twitter medium. Design a simplified version of Twitter where users can post tweets, follow, unfollow another user, and are able to see the 10 most recent tweets in the user's newsfeed. Your design should support the following methods. Post tweet user ID, tweet ID, compose a new tweet. Get newsfeed user ID, retrieve the 10 most recent tweet IDs. Here again, it's like kth recent, kth largest, kth closest. So here we have 10 most recent tweets ideas in the user's newsfeed. Each item in the newsfeed must be posted by users who the users have followed, or by the user herself or himself. The tweets must be ordered from most recent to least recent. Follow ID, follow EID, and unfollow. And then we get a lengthy example here of a new Twitter bot, and then I got post tweet, get newsfeed, follow, post tweet. and get newsfeed and unfollow and then get newsfeed, and then we expect certain outcome from that. And then the last one is get the kth largest element in a stream. Easy. Design a class to be the kth largest element in a stream. Note that it is the kth largest element in sorted order, not the kth distinct element. Kth largest class will have a constructor which accepts an integer and an integer array nums, which contains initial elements from the stream. Each call to the method kth_largest_add return the element representing the kth largest element in the stream. Example, k equals 3, r 4, 5, 8, 2, kth largest, new kth largest 3 of that array. Then whenever we add a new element in there, we would have a different return value, right? So we always get the third largest element here. Add 3 returns 4. Add 5 returns 5. Add 10 would still return 5. Add 9 returns 8. And add 4 returns 8. You may assume that num's length is greater or equal than k minus 1 and that k is at least 1 if not larger. So with that in mind, let's have a look at the theme, which is heaps, also known as priority queues. Specifically, if you do your implementation in C++, priority queue is the keyword for the heap. And then it's basically key to always ensure that your queue has the right sorting, if it's max or min. A heap is a tree-based data structure in which all the nodes of the tree are in a specific order. And then further down they specify that in most cases you have two children, so it's kind of as like a binary tree type structure, also known as a binary heap. And so since a binary heap is a complete binary tree with n nodes, meaning that only the last level has less than the complete amount of nodes, you are guaranteed that the smallest possible height is a logarithm of 2 for n of the number of elements. So basically it all comes down to just like having a sorting where like the top element in the tree is largest, and then all the children are always smaller, which is like kind of the key thing there. And that their children are smaller than those children. So now let's have a look at the problems again that we were encountering at the very beginning, 4 of them, and see how the main theme of heap can be used and applied to all of those 4 problems in their own variation, and what keys to look for actually. So that one problem was about reorganizing a string. You remember we had to have a string with different characters, and we had to reorganize it in a way such that the return string will not have 2 characters adjacent to each other when they are the same character. So no 2 A's next to each other. And the way this can be solved is using a heap or priority queue, where we basically push in a pair of character and its appearance in the string, such that we get it sorted and ordered in a way that the character that appears most is on top of the heap, and then the character that appears second most is second in the heap. And this really helps with the strategy that we basically first take off the most occurring characters one by one all the time before we go to lesser known characters, and just try to like fit them all in next to each other. Like if we have an occurrence of a lot of A's and B's, we would first do A, B, A, B, A, B, and then feed in a C when the C would be like the next most occurring element. And in doing so, we decrease their remaining appearance up until we have reorganized our string such that the overall number of elements is of characters is the same as in the original string. So for that, we initialize a priority queue and push in the elements from a map that we have created beforehand. That map maps character to occurrence, right? So if we have a string that has several A's, then we just have like one A in that map, and then we just tally up how often that A appears. We go through that map and then push the character and its number of occurrences into the priority queue, and after that we basically can assume that on top, at the front of the priority queue, we have the most occurring element, and second element would be the second largest. That's basically the premise of what's going on here in this while loop. So while we still have elements in the priority queue, we keep working and taking off one element and taking off the second most element. If by any chance we encounter like only one element left, we will check if its occurrence is only one more time, which is a good thing, right? If only there's one element left and it can only occur one more time, then we just put it at the end. However, if it occurs twice, that means that we have a scenario where we have like the letter A still appearing twice, and there's no other way to rearrange the letters such that we can fit another letter in between. And in that case, we have to return the empty string, meaning that we didn't find a solution. In any other case, we take the topmost element and we take the like second top element, take them out, and then pushing that into our answer string. Like answer is basically our string, we just like push all those characters in there. Like remember, if A has, we have a lot of A's, have a lot of B's, and like A being the first element in the priority queue and B being the second element in the priority queue, we would just like push an A, push a B, push an A, push an A, and in doing so, then we will update the remaining occurrence of that element in the heap up until we only are down to 1. And if we are down to the last element, we have used up that element, then we're not pushing that into the queue anymore. That's basically what we're saying here. Decrease, and if it's still larger than 0, then still push it back in. That's the whole magic behind the reorganization of the string. Simplest heap, again, is like probably like the standard solution to anything, just like build a heap and then like pop its top element or pop its k largest or k smallest element, depending on if you build a max heap or a min heap. And in this case, basically we build a heap such that the element with the smallest distance is on top of the heap, and then in increasing order we have the second smallest, third smallest, etc. So what this code basically does is just like go through all the points, perform the Euclidean distance operations, and then put this into a vector of numbers, and then heapify those numbers, basically put that into a heap structure, and then depending on how many elements you want, defined here as k, you just pop from the top of the heap k elements and then just put them, or like print them out or return them, depending on how we want the data to be handled, up until we have reached k elements. And that's all to it there. The Twitter design comes, of course, with a lot of data structures for this and that, like users and posting tweets, etc. Assuming this is like basically all legitimate, we will only focus on getting the newsfeed, which again is like the 10 most recent tweets that we want to return. So assume we have already like some data structure going for the users and which user has posted what in terms of tweets. It's just now a turn of how to organize those tweets. And for that, we basically initialize our priority queue with a greater relationship, meaning we build a heap where the tweet time is, I think, like decreasing, and the tweet time, the higher the number, the more recent we will get to the actual current time. So we build up that heap, and then we push into that heap, which is basically everything that's going on in this for loop. We go through all the users, get their tweets, and then push them into the heap. As long as the heap size is smaller than the overall heap size is smaller than 10, we can just feed in. Like 10 being like this hard-coded number, but again, it can be any k numbers of elements that we want to keep track of. Push all those tweets in, and then whenever we encounter the n+1th or the 11th element, we check if the time of the tweet is more recent than the most recent tweet that we have here. If that's the case, then we pop the front of the heap and then push that new tweet in there, and then ensure put it in there and then ensure that the heap structure still holds after we perform that operation. And in doing so, we can go through all the users and all their tweets, and at the end of this logic, we still have a heap structure that holds the 10 most recent elements, regardless of from which user they came and when the user posted them respective in their own tweet. And then all there is to it is basically we just go through the priority queue and empty it, just one by one, put the frontmost element, push it into a vector, and then since the frontmost element is the most recent element, you kind of have a reverse order going on, so that means you have to reverse it one more time to get an order from most recent to least recent in the end when you return it. And that's basically the whole process, using the priority queue or the heap to keep tally of the k most recent elements in your Twitter structure, the tweets. K's largest elements in a stream, really simple priority queue solution, is basically just the definition of the heap itself. We initialize our heap, we take in the number of how many elements we want to keep track of, kth, and we initialize our queue with the int and vector of int, and then a relationship called greater. And as we go through our list of elements and pushing that into our priority queue, we will go through the lists and check if the size is still larger than the amount of elements that we want to keep. Then right now we're only interested in the kth element, not all the elements up to k, which is a simple way to be achieved with the heap. All you need to do is basically just like pop the elements before k and disregard them. Pop and ignore, pop and ignore, pop and ignore up until you have the kth element landing on the top. Then you take it and return it. And that basically is all there is to it. The whole initialization of the priority queue data structure, interestingly, appears here in the constructor. Like once an instance of the class k the largest is, like once an object is instantiated with k and all the elements in your stream of numbers, we set our member variable kth with k, and here q, our priority queue, is established in the constructor from our vector of numbers from begin to end. So we just push them in here, and after the constructor has been finalized, we have already a priority queue going. Basically, our solution is held in there already in queue. And again, since we're only interested in the kth element, all the elements from 0 to k minus 1, like from 1 to k minus 1, can be disregarded, which is what happens here in that while loop. We just like pop them all and kill the qth element out of it.